Well, I've just balanced a whole lot of dominoes up, and what I wanted to do is look at how computers actually do maths for us. How on earth can a mechanical system, like just a chip in a computer, how can it actually do arithmetic? This is my input domino here. If I bump the input domino, it's going to send a signal down the chain. And normally you just have a one single chain of dominoes. So I've mixed it up by, well, initially splitting the chain, which in itself is not that controversial, but then the shorter arm over here knocks out some of these dominoes. So if these dominoes come toppling over, it'll bump these two out, and this won't be able to cross. So in fact, this is a circuit that stops itself. If I bump this and it starts going, this will get there first, knock them out, this will come to a halt. These are my output dominoes. This is the kind of the output from the circuit. That will not fall over. If I now have two inputs, so if I only knocked over this second input, all it would do is these dominoes would all fall over, it would bump these out, and then it would stop, nothing would happen. So it means individually, either one of these bumped by itself, that domino will not fall over. In fact, if I don't bump either of these, that domino will not fall over. So if I knock both of them together, this shorter one here will come along and knock these out. This one at the same time will be coming along, it will split, but when this one gets here, these dominoes are already gone. So it stops, which means these dominoes don't move. This one will go all the way around, it comes along here, comes down here, straight across, and then out. So this circuit, the output only falls over if and only if I bump both of these. And so we call this an AND circuit. It's got two inputs. I have to knock over one of them and the other one to get an output. I tell you what, I'll do knocking none of them first. There you go, that worked. Now the boring one is just this input, because that will just knock that out and stop. The fun one is either just this one, so it stops itself, or both of them so the signal goes through. What would you like?
I think on behalf of the viewers, they're going to want to see both.
Yeah, are you ready?
Yep.
Here we go, one and the other. There you are. So it worked. So we got an output because I did one and the other one. This is a working AND circuit. Now, we can describe this mathematically, so we're not quite adding numbers yet, but it's a good step in the right direction. So we'll call this one input 1, and I'm going to label that one there, input 1. This one here can be input 2, so that's input 2. And then over here we have the output, so I'll label that output. And what I'm going to say is if a domino is standing up, then nothing's happened yet. We'll call that a 0. If it falls over, we'll say it's becoming a 1. So if you don't, the first input doesn't fall over, the second input doesn't fall over, the output in theory should not fall over. If input 1 falls over, but input 2 doesn't, the output won't fall over. If input 1 doesn't fall over, but input 2 does, the output still won't fall over. And then finally, if both of these fall over together, the output falls over, and we call that, this is the logic table. And so this is what's called an AND, actually I'll label it up here, this is a AND gate. So what I'm going to try and build next is a thing called an exclusive OR XOR, which is the best name of a gate. You have input 1, we're going to have input 2, we're going to have our output again. This time, well again, if I don't touch any of the inputs, I don't want the output to fall over. Now, if I only bump input 1, but not 2, I still want the output to fall over, so input 1 has to go through the circuit. If I don't hit 1, but I do hit 2, I still want the output to fall over. And then, controversially, if I bump both of them together, I want them to somehow cancel out in the circuit, so nothing comes out. And that's why it's called an exclusive OR. It's one input, all the other input, but not both. That's the exclusive bit. So I'm going to try and build an exclusive OR circuit out of dominoes. Give me a second here. There we go. So this is my exclusive OR gate, and as you can see, if you bump over just input 1, it'll come flying in here, it goes into the fork here, it'll come along this way, it will then go out here. We don't care if something comes back up the circuit, that's fine. More importantly, it comes around this way, around there, and then out. And likewise, because it's symmetric, if I bump input 2, that goes along into the fork, goes along the middle, comes around here, and then out the output. So either one by itself will make it through the circuit. Importantly though, if I bump them both simultaneously, they will be using the center at the same time. They will collide and stop, and the output won't fall over. I quite like the doing both together, right? Because that's the difficult bit, because anyone can make a circuit where both inputs lead to the same output. I mean, that's easy. One where that happens and they can stop each other, that's where it gets fun. So I'm going to give it a go. Unfortunately, dominoes do fall over quite quickly, and you want to have as much time as possible to enjoy the experience. So what we might do is put on some ridiculous lights and do the whole thing in slow-mo. Okay, right, okay, that should be adequate light. So we'll get this going, and in theory they will cancel out right in the center. Okay, here we go, one and the other one. Yes! Okay, so you can see this guy is dangerously close to going. So when this collided, there was a bit of a recoil back up, but thankfully, again, not quite enough to bump these off going in the other direction. So there you are. It's an exclusive OR. Together, they didn't get through. So we've done the AND gate and made that work. We've done the exclusive OR gate. That's worked. What we're going to do now is go another step in the direction of ridiculous. We're going to have input 1 again. We're going to have input 2. Well, then over here we have the output. Now, again, these are our standard options that we have every time. They're all 4 ways you can bump over 2 inputs. Now I'm going to have output 1 and output 2. Output 1 is going to act as if it was an AND gate. So we'll have that happening. Output 2 is going to act as if it is an exclusive OR gate. And what that means is if you can have both of these outputs for those 2 inputs, these are counting the number of inputs that get bumped. So this is like a units column, this is the ones column, and that's 2s. So if you only bump 1 input over, the 1 output goes. If you bump both of them over, you get the 2s column goes. And so this is a very, very basic circuit that can count. It can tell if you bump just 1 or 2. It doesn't matter which bump, it can still count it. So if I repurpose, because it needs an exclusive OR in the middle, if I very carefully... This is called a binary half adder. And the reason it's called a binary half adder is it's doing half of what you need to do full binary arithmetic. So if you can build what's called a binary full adder, which believe me we'll get to in a second, then you can do all the calculations you want. So a binary full adder is what calculators use, it's what computers use, it's the basis of all automated computation. All right, so I'm almost finished. I'm putting the last 2 dominoes in over here.
That's a monster, man.
It really, you know, well, this bit's interesting because this chain splits off, and all it does is zigzag backwards and forwards for a while. And the reason I had to go and do all these extra, because I could have just done that, right? The reason I had to do all these extra dominoes is because this is a delay line. So I need to give, because you can still see the exclusive OR is in here, I need to give the exclusive OR enough time to do its thing before this signal catches up with it. So this is just delaying one of the signals. The way this works is if I just bump this input. Oh, first of all, if I bump none of the inputs, perfect. If I just bump this input, it will come in here, goes into the fork, goes across the exclusive OR, comes out the other side. This waste signal just comes back and out, that doesn't matter. Goes around here, goes around there, and then it goes out the unit output. So that means that 1 input was bumped. If I bump this one, now this is where it gets slightly more complicated. Here it splits. And then 1 signal goes through the exclusive OR all the way through, out the other side, comes around, comes here, splits, goes out the units output. Also, it blocks these. So this fork, so this one stops this chain. Meanwhile, the other signal's coming along here, it gets to here and it's stopped. So either one by itself, only that output falls over. If I bump them together, well, this one splits again, that one goes that way. This one's coming in, they collide in the middle and stop. This one carries on its merry path, gets right to the end, goes straight out that output, and this one falls over, but that one doesn't. And so that's the 2's output. And so that's the binary number that counts how many of these dominoes I bumped. This is a circuit of inanimate objects that can count.
That excites you, doesn't it?
I get disproportionately excited. People say, oh, I want to know how computers work. And they mean, I want to know how to use Microsoft Word, or I want to know, or even programming languages. People go, I learned to program that. Or people go, you know what, I do everything from the terminal prompt. Right? But you're still just interacting with the software level of the computer. How is the computer actually executing what you're telling it to do? And right down at the very bottom, this is the absolute fundamental layer of all computing, is a circuit of objects that can make decisions based on inputs. All right, so I'm going to bump just this one. Only that will fall over. That won't move. Here we go. Ready? The system works. Look at that. So it is able to stop this one from coming through. The exclusive OR worked perfectly. This came through without being stopped. Went out. There's our units output. This one didn't move. If all you saw was this, you would know that back here I only bumped one input, not two. All right, so that worked. Now, as I said, this is just the half adder. We want a binary full adder, and to have a full adder, you need to have three inputs. So you'll have input 1, input 2, and input 3. And so now we need every single combination of, there's not bumping all of them, there's doing that, there's doing that, there's bumping those, there's bumping that one, but not those, there's that one, that one, that one, that one, that one, that one. Okay, there we are. So that's all 8 ways you can have 3 different inputs falling over. And now I'm going to label this. This is going to be our 2's column, and this is going to be our 1's units column. So this is our binary counting of how many we bumped. So there we've bumped none of them. There we've bumped just one, 2 of them, 1 of them, 2 of them, 2 of them, at the very end, 3 of them. And to have 3, we'd expect that to happen. So if we could build this circuit, we would have the full binary adder. And you can build this, right? So all you need is basically you chain together 2 half adders, which is why that's called the half adder. So with a little bit of careful position, you need a lot of dominoes at this point. You need maybe 2,000 or 3,000 dominoes to make this work reliably. You could make a massive circuit which does this. And once you can do that, you can then add any binary numbers together that you want. Shall we do a calculation? Shall we? I'll tell you what, do you want to give me 2 numbers between 20 and 50? What should we do?
Let's do 42.
Yeah, of course.
And 17.
And, okay, so right, so we're going to add 42 to 17. A bit of a spoiler alert. We're expecting 59, just so we're all, don't want to ruin it for anyone. But, okay, so I'm going to turn these into binary numbers. So 42 is going to be 32, which means I need another 10. So 32, no 16s, 1 8, no 4s, a 2 and a 1. And then down here, 17 is 0, 1, 0, 0, 0, 1. So that's 42 and 17 in binary. And so now, and they're incredibly boring numbers to add in binary.
Why?
Oh, because if I go along and add them together, what's 0 plus 1 is 1. 1 plus 0 is 1, 0 plus 0, 1 plus 0, 0 plus 1, and 1. So at no point did you having to add 2 1s together. Right, so that made the sum, which is, that's what we get for choosing random numbers. But we can double check the system works, because now that's, for label, that's units, 2s, 4s, 8s, 16s, 32s. Our answers are 32 and a 16, which gives us 48, plus another 8, which gives us 56, plus a 2, which gives us 58, plus a 1, which gives us 59. So that is 59 in binary, right? So the system works. What could have happened though, let's just rig it with some interesting binary numbers, right? If I had, let's say, 1, 1, 0, 1, 1, 1, and I'm adding it to 0, 1, 1, 0, 1, 1, right? So I've deliberately lined up loads of 1s to get in the way. Because now, if I do 1 plus 1, the answer's 2. And I can't write a 2 down there because it's binary. But what I can do is I can write the 0 and carry the 1. And so now I've got to add 3 of these together. So I've got to add, okay, 1 plus 1 plus 1 is 3. So I write the 1, carry the 1. Okay, 1 plus 1 is 2. So put that down there. And every single time, the only, oops, that should be a 0. The only option I can have is either, I'm only ever adding combination of 3 1s and 0s. So no matter how big the numbers are I want to add, I never have to do anything more complicated than 3 1s and 0s. And this is every single option. So the reason that binary is great for adding is when you're adding base 10 numbers, you might have to add a 2 to a 7 or a 1 to a 4, an 8 to a... There's so many options that you may have to add. Binary, only those 8 options. If you can do all of those, you can add any numbers together by just doing that one step over and over and over and over and over again. So if you can build that at Domino's, that's one bit of the calculation. So if you built this, I don't know, 4 times. So if you had, you'd probably need about 10,000 dominoes. If you had 10,000 dominoes, you could build the full adder circuit 4 times in a row. It means you could take 2 4-digit binary numbers as inputs, and you could have the 5-digit sum coming out as the answer.
Of course, imagine if someone did that.
I mean, you'd have to be truly insane to phone up a series of domino manufacturers, find a wholesaler who would ship you 10,000 dominoes, find a concrete floor at the, at the Museum of Science and Industry in Manchester, and then spend an entire weekend balancing dominoes. I may have done this. I got some friends together, we got 10,000 dominoes, and we built a circuit which will add 4-digit binary numbers and give you a 5-digit answer.
So if you'd like to see Matt's giant domino computer in action, there'll be a link on the screen and in the video description. It's obviously well worth a look. There's also more of my interview with Matt where he talks about how you take this domino idea he's just explained to the next level. It'll probably be unlisted, so having watched this video for so long, you're in a very exclusive club that will know about it. And finally, I'm sure some of you will be saying in the comments, why isn't this video on Computerphile? Well, it probably could have been, but here it is on Numberphile. Those of you who aren't wondering that because you've never heard of Computerphile, allow me to take this opportunity to tell you about Computerphile, which is kind of like the sister channel of Numberphile, all about computer science and those sort of things. It's well worth a look, and again, I'll include links. There's going to be loads of links under this video, so why don't you sort of extend it and make that information box a little bit bigger, and you can see them all sitting there.